welcome back to my YouTube channel. So we are actually in part 2, chelate effect, from the topic of stability of complex ions and chelate effect. So what is a chelate effect? It can be defined as entropy changes that accompany the formation of coordination compound in solution. So what is an entropy? It is actually a degree of randomness. Alright, so as a general rule, a complex that having bidentate or polydentate ligands are more stable than an equivalent complex having monodentate ligands only. So I have explained a little bit about this general rule in part 1. Okay, so the bidentate and also polydentate ligands are also, we call it as chelating agent. Okay, so why? Because of their ability to hold metal atom like a claw. So let's say this is your metal, this is your ligand. From bidentate or polydentate, it will claw, okay, or it will coordinate to the metal like this. Okay, alright, so chele is from a Greek, okay, means from Greek meaning claw, right? And chelation actually confers stability to a metal complex. Okay, other than that, chelate effect also can be defined as the unusual stability of a coordination compound involving a chelating multidentate ligand, okay, as compared with the equivalent compounds involving monodentate ligands. So here we have an example of nickel, okay, nickel ion. Alright, so the added stability of a complex that results from the formation of a chelate rings. Okay, for example, here is nickel 2 plus. Alright, and we have one monodentate ligand, which is ammonia, and the K1 here is 10 to the power of 28. Okay, so and the overall reaction here is the, for example here, alright, the beta 2 is 1.0 times 10 to the power of 5. Okay, so alright, okay, here this is a displacement of 6 monodentate ligands. Okay, here we have two kinds of reactions, reaction 1 and also reaction 2. The difference between these two reactions is, okay, the types of ligands. Alright, so reaction 2 involve with 6 ammonia or 6 monodentate ligands, while for the reaction 2 we have a 3 En or 3 ethylene diamine. Okay, so okay, let's look at the beta, okay, or the overall formation constant for reaction 1, where the value here is 10 to the power of 8.6. Alright, while for the reaction 2, okay, we have beta 3 instead of beta 6 because we already have a 3 ethylene diamine, where each ethylene diamine contains 2 nitrogen. Okay, alright, so the beta 3 here equals to 10 to the power of 18.3, which is much more larger compared to the reaction number 1. Okay, so here these actually relative signs and also the magnitude of contributing to the delta H and also T delta S. Okay, alright, so here this is where we have the nickel 2 with ethylene diamine, okay, to form this structure or this complex ion, where we have the 2 nitrogens actually attached to the nickel, and the formation constant here is 3 times 10 to the power of 7. And another example, if we compare with the first reaction with the second reaction, where the nickel 2 plus, okay, we react, okay, this nickel 2 plus with 2 molar or 2 ammonia here, okay, to form this complex ion, and the beta 2 here is 1 times 10 to the power of 5, okay, where this value is much more smaller compared to the first reaction here, okay. So it can be concluded that the nickel with ethylene diamine is 300 times more stable, okay, than the second reaction due to the formation of a chelate ring. So this is the chelate ring, okay, alright, where it looks like a claw, okay, coordinate to the metal ion. Okay, so why does a chelating result in greater stability? Okay, we have a few factors. The first one is the effective concentration. Okay, so this is the nickel with ethylene diamine. Okay, because the ethylene diamine itself has 2 nitrogens. Okay, alright, the first and second here, okay, is the second nitrogen is held close to the metal by the this group, alright, allowing the second bond to form easily. Okay, so if we compare with the monodentate case, okay, nickel with monodentate ammonia here, the second end, okay, this is the second end, must keep moving until it comes within close proximity to a metal, proximity of a metal to bond, okay, where it is likely to form the second bond with the nickel 2 atom. Okay, so if we look at the first and also second one, okay, the first one with the bidentate, we have higher concentration of donor atom, alright, compared to the monodentate reaction here. Okay, so this is, we call it as a bite angle. Okay, other than that, we have a 4, 5, 6 and also 7 membered ring. Okay, and 5 membered ring are generally more stable than the 6 membered rings. Okay, alright, so the 4 membered rings are much more rarer as they suffer from the bond strain. Okay, so the order of stability is as follows. Okay, we have the 4 membered, okay, 1, 2, 3, 4. We have the 5 membered ring, 1, 2, 3, 4, 5, okay, that connected the ligand here, okay, the 2 ligands, okay, form a 5 membered ring, okay, alright, coordinate to the metal. And then we have a 6 and also 7 membered ring. Okay, so for the 4 membered ring, we have, or it has, okay, it has too much strain within the bonds to make a 4 membered, while for the 5 membered ring, they are the most stable, okay, since the bond strain is less and the ligand allows for an increase in bonding ability. Okay, while for the 7 membered ring, okay, increase in bond strain, okay, because okay, if you compare it to the 5 and also 6, okay, alright, we have increase in bond strain, and in this case the second ligand is a little further away, okay, alright, so it is not likely to bond, okay, compared to the 5 and also 6 membered ring. So when the rings become much larger than 6, okay, the enhancement of the local concentration is diminished. Okay, ligands are positioned further away from the metal in a larger rings. Okay, second one, other than effective concentration, is the entropy consideration, where we have the degree of randomness. Okay, so in this we have 2 examples, okay, A and also B. if you look at A first, okay, we have no change in the number of particles where the delta S is equal to 0. Why? Okay, here this is one okay, this is one compound. Okay, this is 2 ligand, 2, and this reaction between 1 and also between this nickel with 2 ammonia here will produce 1 metal complex and also 2 H2O. Okay, so 1 plus 2 equals to 3 and 1 plus 2 equal to 3. So we have no change in the number of particles. Okay, alright, the product and the reactants are both we have 3. Okay, for the B, okay, what happened here? We have 1 and also 1 here. Okay, let's say they are particles. Okay, we have 2 particles here. While for this one, okay, for the product we have 1 and also 2 here. Alright, so the reactants are actually 2 and the products here are actually 3. Okay, so we have an increasing number of the products. Okay, so 2 particles produces 2 particles produce 3 particles. And what happened to the delta S? Okay, what happened to the entropy? Okay, the positive, alright, value here which increases disorder, okay, degree of randomness. So the forward reaction is favored. Alright, and then when the delta S is positive, then the delta G will become more negative. Okay, so here we have another example. Alright, so for the first one, 7 particles and there is no change in the production of the products. Okay, we have also 7 products and the beta value here is 10 to the power of 8. Well, for the second one, okay, this is monodentate. Okay, it involved with monodentate ligand. Right, 6 monodentate ligands, while this second example we have bidentate ligands. Alright, where from the reaction, okay, from the reactants, okay, we have 4 particles and they produce 7 particles for the product. Okay, where the value is 10 to the power of 18, much more larger than the monodentate ligands. Alright, so the larger the number of particles distributed randomly, so the higher the entropy of the reaction, the higher the degree of randomness of this reaction. So back to the formula where we have the delta G equals to delta H minus T delta S. Okay, so here we have a large increase in the delta S result, okay, where the delta G will become more negative. Okay, so this one will become more negative. Okay, since where we have the delta G equals to negative RT ln K, so a more negative delta G leads to a more positive equilibrium formation constant. So, okay, what is the delta G, delta S and delta delta H? Delta G is the Gibbs standard free energy, while for the delta H is the standard enthalpy change, the energy. Okay, alright, the energy change. While for the delta S, okay, delta H, it can be positive or negative, alright, and then the delta S is the standard entropy change, and the T must be in the Kelvin, and the R, okay, the gas constant is 8.314 joule per K mole, and K is the equilibrium constant. Okay, so here we have a data given for the cadmium 3 complex ion with 3 different situations, okay, that show and one of these A, B and also 3 C show the greatest stability of chelated complex, okay, compared to its non-chelated analogues, okay. So if we look at the value for the B4 beta 4, so C has the highest value of the log beta 4 with a 10 to the power of 3, where it is actually has the highest thermodynamic stability. Oh sorry, this one is the delta H and this is the delta S. But if we look at the delta H, okay, of this A, B and also 3, they are almost similar. Negative 52.5, negative 57.3 and also negative 55.7. So therefore, okay, as we can see from A, B and also C, extra stability of the chelated product has over the non-chelated product is not enthalpy driven, okay. And then for the delta S, if we look at the delta S here, okay, where the C has the largest or the largest value of the delta S here is the positive 10.4, okay. So this C actually produces the most positive entropy change, and it can be considered as entropically driven, okay. So A, B, C, A and B involved with monodentate ligand, okay, while for the C it involves with 2 ethylene diamine, okay. So this is a bidentate. Alright, okay. So alright, so that's all for part 2. I'll see you guys in part 3. Bye.